if they are out there, they would give this signature and we would see it potentially.
Warp drives have been a staple of science fiction for decades. In the 1990s, Miguel Alcubierre described them scientifically. But recently, a paper was published showing that if an alien civilization built a warp drive, we might be able to detect it using gravitational waves, ripples in the fabric of space-time. And this work has implications beyond mere flights of fancy. So I headed to Queen Mary University, London, to talk to its lead author about warp drives and the relationship between sci-fi and fundamental physics. Katy, you're a physicist that's worked on warp drives. I mean, we've seen this in sci-fi movies, but what is a warp drive? How would it actually work?
Yeah, so a warp drive is a really clever idea. So normally when we think about propelling a spaceship through space, we're using conservation of momentum. So we're using the fact that we're burning some fuel and firing out the back of the rocket, and that will propel the rocket forward. But a warp drive is a completely different idea of how to move a ship through space. So the idea is that we use this idea of space-time curvature that comes from Einstein's theory of general relativity, and the fact that space and time are somehow flexible. So what we aim to do with the warp drive bubble is to have a region in front of the ship where we collapse space-time, where space-time contracts in front of us, and then the space-time behind us expands to kind of counteract that. And by doing that, we actually move through space. So it's like, if you imagine the space between me and the camera is contracting, I sort of be pulled towards you. But from my perspective, I wouldn't feel any kind of acceleration. I would actually just be sort of sitting, as if no forces were acting on me. And I'm just sort of pulled through space by the fact that, as I say, space itself is contracting and expanding around me. Really what the warp drive is doing is a bit like a wormhole. It's kind of creating a shortcut through space-time for me to get from A to B quicker. So by contracting the length, I can still travel at a speed that's the speed of light, but I travel a greater distance, right? So the distance is contracting. The time it takes me to get from A to B is shorter than it would be if that distance was still longer.
So where does this idea of a warp drive come from? Was it the sci-fi first or the science?
It's actually one of these nice ideas where actually it was sci-fi first. This idea was in Star Trek. And so Miguel Alcubierre, who was the scientist who first proposed this warp drive metric, he was a Star Trek fan. So he told me, when I met him recently, he told me that at Cardiff, they used to watch Star Trek every Thursday evening together in the group. This was a sort of fun activity. And then he was working on space-times, numerical evolutions of space-times. And he had this idea for, well, how could you actually get this warp drive that's being used in Star Trek in a way that actually is consistent with this theory of general relativity. And so he had this idea of kind of surfing on a wave in space-time. And that led him to develop this idea of contracting the space in front and expanding the space behind. So as I say, it was really something that came out of science fiction and influenced science. Actually talking to people who are scientists, they do actually still watch all of these programs. So there's certainly a lot of nostalgia value in watching old episodes of Star Trek. And it's a great world, right? It's a world where science is kind of almost the key goal of most people's lives. They don't have money anymore and they don't have sort of fighting, although there is still some fighting, but science really drives what they do. So I think in that sense, it is inspirational.
So in Star Trek, you often hear the phrase, warp signatures detected.
Exactly.
Seems like you're saying there actually is one. Tell me, how did this work start? What were you trying to do?
Yeah. So, I mean, it started as kind of a fun project. So in fact, it started in my office in Göttingen in Germany when I was a postdoc there. And I had two postdocs visiting me, so Sebastian Kahn and Tim Dietrich. And actually, Tim, I think, noticed that I had a Klingon dictionary on my bookshelf. And he said, "Oh, you have a Klingon dictionary. I have a Klingon dictionary." And Sebastian said, "Oh, I don't have a Klingon dictionary, but I have like the Encyclopedia of starships or something. So we all realized that we were all big Star Trek fans. And we had been thinking about projects that we could do together. And I think Sebastian suggested, oh, well, why don't we do a warp drive? Because there's this warp drive metric that Alcubierre developed, and maybe we can simulate that and see what happens. And we immediately hit on a problem in that if you just simulate this warp bubble that Alcubierre suggested, it actually doesn't generate gravitational waves. So if it's stable, if it just stays there and it's traveling at a constant velocity, you don't generate any gravitational waves. So you wouldn't see any signal from that at all. But actually, you don't know a stable solution for this Alcubierre metric. So if you put in any kind of normal behavior for the matter that drives the warp drive, it will collapse and it will disperse. So at first we thought this was another problem, but then we realized it was both a feature and a bug. So we were like, well, we can do what happens always in Star Trek, where you have some warp drive containment failure. So whatever is usually holding this bubble in place has somehow broken down. And then we see it, dispersing, and having, this sort of explosion of the warp bubble. And that will definitely generate gravitational waves. In fact, will generate a huge amount because it's very messy. So as soon as you have matter moving around in a kind of messy way, you'll always generate gravitational waves. So yeah, we decided to motivate it as kind of the, catastrophic situation where the warp drive breaks down, see what would happen in that scenario. What would be the signatures in gravitational waves?
Is there any other way to generate gravitational waves from a warp drive? I mean, what if they just accelerate, decelerate it?
So acceleration and deceleration would work. Acceleration and deceleration would give you gravitational waves, but it would give you probably something that was relatively monochromatic, so just a single frequency, which would be related to the timescale of your acceleration. So the problem with simulating that is you actually need to. So in the simulations that we do, everything is consistent. So everything actually is really generated by physical equations. And so the behavior of the matter has to also follow dynamical equations. And to get it to accelerate, we actually don't know what the dynamical equations for the matter would be to get it to accelerate in a stable way. So in fact, it was easier technically to make it just collapse rather than to make it just accelerate at a constant rate.
You found there's a gravitational wave signature that in principle could be detected. Is that like a moment of wow, or is it just very slow?
It is generally fairly slow. In this project, there was a moment where it was really exciting, where we got it working. So at first, as I say, nothing really worked. Our gravitational waves just looked super messy and they weren't converging in the right way as you went to larger radius and things like this. All the kind of technical checks you do just weren't working. And a paper came out that suggested a different way of dealing with the coordinates in the simulations. And we thought, okay, we'll give it a try. Who knows, it might work. And it just fixed everything in this one go. So, I was actually sitting at a conference with Tim. We were both at the same conference and I was running the simulation. Okay, I'm going to try this new gauge condition. And the signal came out and it was just perfect. And so I was, I turned to Tim, I was like, look, it's working. And that was a really exciting moment. But then after that, you have to do all of the kind of, checking and making sure everything works and trying different scenarios. So after that, it sort of slowed down again. And then towards the end, it was exciting as we were writing the paper. And I think we were realizing as we were writing the paper that it was exciting in a way, the idea that you can actually potentially see alien signatures from these things, all of the caveats about can you build them and things like this. But, if they are out there, they would give this signature and we would see it potentially. I do feel that it's kind of worth looking for.
I've only studied warp drives that go slower than the speed of light. Why is that?
Yeah, well, so simulating warp drives that go faster and faster, the amplitude and the gradients in the simulation get a lot bigger. So everything gets a lot more difficult to simulate. We need a lot more resolution. And since we were already being a little bit cheeky in using our scientific allocations for doing these warp drive simulations, we didn't want to push it too much. So we didn't want to use too much of our computing budget on doing warp drive spacetimes.
So coming back to gravitational waves, what kind of signal would you actually be looking for? Is it weak? Is it strong? What kind of frequency range are we looking at?
So we have to kind of caveat the simulations that we did. So we had to make particular choices about what matter was driving the warp drive, the size of the bubble and things like this, and the shape of it to some extent. So a lot of the results that we get are dependent on those kind of choices. If the aliens make different choices, we might see a different signal. But I think something that was kind of robust in all of the things we did was that the size of the warp bubble kind of tells us what frequency of gravitational waves we're going to see. So if you have a bigger bubble, you see a lower frequency of gravitational wave. A smaller bubble gives you a higher frequency of gravitational waves. So what we saw was really something that was very dominated by this one frequency coming from the size of the warp bubble. Yeah, that would be the thing that we would look for, is really some unexplained signal with some frequency content that was dominated by a particular frequency.
And then what kind of frequencies can we detect now? Is it the sort of frequency that a warp bubble would give off?
Well, so it depends what you so this was a bit of a disappointing fact when we did the simulations and we understood how it worked, is that if you work out the frequency that you get for a kilometer-sized warp bubble, which is kind of consistent with the kind of size of Star Trek ships, you find that it's sort of hundreds of kilohertz, and that's much higher than the regimes that we're testing currently with gravitational wave detectors. So most of the detectors we have are sort of looking at the hertz range, and below that actually is the sort of the regime of interest for astrophysical events. And so to see our warp drive signature for as I say, the kind of bubbles that we might think are realistic, although you can debate about what that means, it would be outside the frequency range that we're currently looking at.
And what about the strength of the signal? Is that a factor? Because suppose you built a detector that could detect that frequency. How big is the strain? Could it be, is it within conceivability?
Yeah. So this was one of the interesting things that we discovered, is that, so that signals for gravitational waves get weaker as the source gets further away. So you have to specify where we're looking at it. But if we say it's something within our galaxy, which is already, looking at a reasonable volume, or even out to sort of the Andromeda galaxy, which is our neighboring galaxy, the strain signal is very strong. So it's comparable to the kind of detections that we're currently making with the LIGO detectors of merging binary black holes. So the strength of the signal isn't a problem. The strength of the signal in principle for things within our sort of local galaxy and local galaxies would be strong enough that we would see something. But it's in the wrong frequency range. So it's like a telescope looking at the wrong frequency of light, and not seeing anything because it's in X-rays instead of in visible light, for example.
I have to say, when I went to the Black Hole Inside and Out conference, they were talking about future detectors and Vitor, Vitor,
Cardoso, yeah.
He was like, maybe we should look at higher frequency. I mean, is there anyone looking at it?
Yeah, I mean, there's an active push to have detectors at higher frequencies. So the pushback against that is always, we don't know of any astrophysical sources that would create signals in this kind of regime. And so, of course, that makes it difficult to persuade anyone to spend a lot of money on a detector. So the types of signals that we might see that are not other than gravitational waves from alien warp drives, there's primordial black holes. So the idea that we might have smaller black holes that are merging, and that would give off gravitational wave signals. And they would be in this higher kilohertz frequency range. And similarly, signals from the early universe, there's a lot of exotic physics that might be happening in the early universe, and that tends to leave imprints at higher frequencies as well.
So right now we've got LIGO, no chance, wrong frequency, right?
Well, you say that, but then, so someone pointed out to us that actually, well, there are two hopes. So firstly, if you had something that was more of a Death Star than a Starship Enterprise, it might work. So people point out, and we said, well, you can't mix Star Wars and Star Trek. So that was our initial response. But I mean, in principle, as I said, it does scale with the size of the bubble. So, I mean, you're getting into huge amounts of energy once you have a bubble that's like 100 kilometers, right? So you need it to be like the size of a moon, right? To start seeing it in the LIGO band. So, maybe we can say we've ruled out like Death Stars using warp drives. But they're within our galaxy. Yes, we always have to caveat sort of within our galaxy or within some observable distance.
Because the galaxy was far, far away. Right?
That's true. The galaxy was far, far away. So we can never say never, right? The universe is very large. But that's one hope. And then there's actually a second quite interesting feature of gravitational waves called gravitational wave memory. And that there's a very slow component of gravitational waves that happens when gravitational waves pass us. They don't actually leave everything where it was originally. So as the gravitational wave passes, the space-time stretches and contracts and expands, and it doesn't go back exactly to where it was. And that's a lower frequency effect. And so the low frequency part of this gravitational wave might actually lie more in the sort of the LIGO band. So there's a potential signature there.
How do you actually go to the different frequency? What is it?
Yeah. So actually, in principle, it's easier to go to the higher frequencies because you need a smaller detector. So, the detector size is also related to the size of the length of the waves that you want to measure. So there are quite a lot of interesting proposals. There's a program called Quantum Sensors for Fundamental Physics. And there's a proposal to use condensed matter systems that would actually be tabletop experiments that you could do in a lab to detect gravitational waves. So that's something where you could have lots of these detectors in lots of labs around the world, and they would build up, together these gravitational wave signatures.
Presumably it wouldn't be easy to actually make a warp drive. What would be some of the challenges?
Yeah, I mean, there are so many problems with the warp drive. Where to start? I mean, the warp drive in the first place, so people often say it's a solution to Einstein's equations, but it's not really that. Einstein's equations, they have curvature on one side, and then matter on the other. So matter curves space-time. And so what we think of as being a solution to the Einstein equations is usually we have some matter like the sun, and then we work out what curvature that creates. But in the case of the warp drive, we're doing the opposite thing. We're saying, I want space-time to curve in this way. So what matter do I need to put in to give that curvature? And then what happens if you actually do the calculation is you find out you need something really strange. So you need what we sort of refer to as exotic matter. You need matter that violates something called the null energy condition, which roughly speaking means you need something with negative energy density. And so the problem that you immediately come across is, well, we don't know how to create large amounts of negative energy density. So actually one thing to note, which I think is always important to note, is that it's not, so we say that there's this null energy condition, but it's not a hard rule, right? So we actually know that the null energy condition is violated by certain quantum processes. So something called the Casimir effect. We see small amounts of negative energy being generated. But this, as I say, this is a quantum effect, so it's on very small scales. So to try and generate enough of this negative energy to curve space-time enough to fit a ship the size of the Starship Enterprise in your bubble, it's going to be problematic. So the first thing is, where do I get all of this negative energy density from? And then, assuming that I managed to do that and I managed to construct my bubble, there are a few issues with it. So if you don't want to go faster than the speed of light, then you're probably okay, broadly speaking. So the issue that once you start traveling faster than the speed of light using your warp bubble, which in principle there's no prohibition to doing that, you'll find that you'll not be able to turn it off. So it's got a horizon at the front of the warp bubble. So if you want to send a signal to the front of the warp bubble to say, turn off now, you'd have to send a signal faster than the speed of light to be able to do that. And so as we were saying, the warp drive doesn't actually locally violate faster than light travel. So, locally light still travels at the speed of light. So I can't send a signal to the front of my warp bubble. So I'll go very fast, but then I'll not be able to stop, which, obviously doesn't seem ideal. And then, even sort of thinking on a bigger scale, there are these issues that come with if I can travel between 2 points faster than some other observer, it's actually a point that's common to things like wormholes, where you have these shortcuts through space-time. You can potentially violate causality. So you can potentially travel in such a way that you can travel back into your past. So you could do something like, kill your grandfather so that you never existed, and you come up with all of these time travel paradoxes. So, just on the face of it, on the equations, there's nothing that actually stops you once you've constructed this warp drive from doing that, from creating one of these, what's called a closed time-like curve, where you can go back into your past. But we really deeply believe that causality should always be preserved. And so there are reasons to think that something would prevent you from doing that somehow, the space-time would become unstable once it started traveling at faster than light speeds.
This is Hawking's chronology protection conjecture, right?
Right, exactly. Yeah. So this idea that, as I say, something would come in and maybe, so actually, it does link a bit to the simulations that we did, that we start to see that once we go to higher velocities, we start to have issues with evolving it. And so what you might find is that small fluctuations in some ways build up and cause the bubble to collapse, before it can actually reach light speed. So something like this, we don't know if this happens, but if I had to guess, that's the kind of thing that I would say would sort of step in to prevent you from creating these kind of paradoxes. My instinct, as someone who studies sort of dynamical space-times, I always feel that there usually should be some kind of dynamical mechanism that prevents you from getting into these kind of situations. I mean, already you've had to generate some negative energy density, so maybe that's the prohibition, that we actually just can't generate that in the first place. Yeah, as I say, I mean, I'm open to all ideas. I would never say no, but my feeling is that at some point before you reach light speed, you develop some kind of instability that will prevent you from getting to higher speeds.
But is there any point in building a warp drive if you can't go faster than light? I mean, maybe it's the only way to go 0.9 times the speed of light. Could there still be some utility?
Yes and no. So I think it's a really interesting way to travel around the galaxy, right? So you are just using the curvature of space-time, but I think if you're talking about efficiency, it's not efficient, right? So the kind of mass of matter, of this negative energy density that you need to generate to drive this warp drive, this warp bubble forward, is enormous, right? So if instead you took that matter and you burnt it as fuel, you'd be able to accelerate your ship to enormous accelerations. I guess one argument for it is that the person in the warp bubble doesn't experience acceleration. So, normally it would kill human beings to travel much above, 1G for a significant amount of time. So I guess one advantage is that, you can actually travel in that warp bubble you'd be as if you were in sort of free fall. So you'd be like in the International Space Station floating around, which I guess would be more pleasant than traveling at very high accelerations.
So if you found a signature of warp drives, would that have any implications for fundamental physics? Like, would material that violates the null energy condition have implications for singularities? Don't they assume that there is no violation of these energy conditions?
Absolutely. So I think it would have if we saw these signals, it would have huge implications for fundamental physics. If you found out that somewhere out there, aliens have figured out how to generate large amounts of this negative energy density of this net violating fluid, that would change our perception of many things. So the singularity theorems rely on the fact that that you have matter that obeys the null energy condition, at least on average. And so, if you found out that that was not the case, then, well, it might offer you a way to explain what happens at the center of black holes, that maybe there aren't singularities, but somehow it's stabilized by some negative energy density, or perhaps it forms a wormhole to go through into another universe. Once you have this negative energy density, you can get these kind of curvatures, which, as I say, are characteristic of things like wormholes. So it would open up a lot of interesting possibilities.
And discover there are aliens using warp drive.
Which, yeah, exactly. Also, discovering aliens is obviously very exciting, which, and a huge paradigm shift for the scientific community.
So some scientists think that building a warp drive is basically impossible. What's your opinion?
So I should say that in our team, we had very different views on this. So Tim Dietrich was very pessimistic. So I have to say on his behalf, since he's not here, that he would be completely against it and say it's completely impossible. I think I'm slightly more open to different ideas. I think that fundamental physics, we actually don't understand everything. We really don't understand things like dark energy and dark matter. We don't have a quantum theory of gravity. So we don't really understand enough to be able to say categorically, no, this can't happen. So I think we should always keep an open mind. I suppose I wouldn't bet a lot of money on being able to create one. But I think, I think we should never say never when we're not sure, right? And we're not sure.
Tim thinks this is never going to happen. Why work with this at all then? What's the point? I think it's just a bit of a fun project, or are there things we can learn about relativity?
Yeah, so I think for Tim, the motivation is the questions that we were talking about with the singularity theorems. So something that we're planning to do next is to take this kind of matter and collapse it and see if we do form singularities, or if we form wormholes, or what we actually, what's the actual behavior. So actually, something that we realized in doing this project was that this hadn't been studied very much. People are rightly kind of skeptical about the existence of negative energy densities, but particularly, once you have formed a black hole and you're talking about very high densities that you would get in the singularity, at that point, quantum physics may play a role, and you may start to break these conditions. And then, maybe we can understand dynamically what would be the consequences if that did happen. So I think understanding the dynamical behavior of this exotic matter is interesting, and it tells us something deep about gravity and how gravity behaves.
But what about, you mentioned black hole singularities, what about the Big Bang singularity?
Yeah, right. So any kind of the singularity theorems really apply the same kind of the same kind of rules apply for both cosmological singularities, so singularities in time, and singularities at the center of black holes, so singularities in space. You could also argue that if you wind back time, you don't reach a cosmological singularity. If these effects start to turn on, maybe the universe bounces. So, there are people who study this, and that's exactly the ingredient that they use. They need to have some kind of material that violates the null energy condition, which you can also have from a sort of modified gravity theory. There are people who seriously study this as bouncing cosmologies, where you go from one epoch to the next through this non-singular bounce.
So what would happen if you flew a warp-enabled spaceship into a black hole? Could you use that to get out again?
This is a fantastic question. So the reason this is a fantastic question is because we don't know the answer to it. And it's actually very interesting, and something that we could actually do a simulation to try and find out. So, you've got the curvature of the black hole, and you've got this warp bubble coming in that's very curved as well. And this is a highly complicated problem. So you can't just sort of put one on top of the other and add them up and say what will happen. It's really nonlinear and dynamical. So you could imagine that, this warp drive somehow disrupts the black hole, or the black hole disrupts the warp drive. And so which will win in this context, it's not really clear. But something that's been done that's actually related to this is actually to throw a wormhole into a black hole, which is kind of the same principle, because the wormhole gives you a kind of a shortcut to get out of the black hole. So although you can't fly out of the event horizon of the black hole, maybe you could use this passage to try and get out. And it was a really nice piece of work to show in what cases you could and in which cases you couldn't. And actually really interesting in the context of these energy conditions, because you could show that there were energy conditions that if you imposed them, you wouldn't still be able to get out of the black hole. And you really had to break what we consider to be one of the strongest energy conditions. So not just the null energy condition, but some, time averaged version of it as well, which most people feel might be more fundamental. And that was the one you had to break to actually be able to get out of the black hole. So it gives us a kind of hint that, maybe to do something really exotic, you actually have stronger conditions than the ones that we currently are considering.
If you flew into a star, does the warp bubble protect you? Or, because in Star Wars, they're
traveling through hyperspace ain't like dusting crops, boy. Without precise calculations, we'd fly right through a star, bounce too close to a supernova, and then it ended real quick, wouldn't it?
I mean, they're not using a warp drive, I know.
They've got their shields. They've got their shields too.
Yeah. But does the warp bubble itself give you any protection?
I don't think it does. So I think that at least if you consider sort of the deformation of space-time is in front of you and behind you. And actually, if you just sort of look to the sides of you, it's basically flat space. So I think there would be nothing to stop the plasma of the star pouring in on either side of from either side and, pouring into where you are and then, burning you. So I wouldn't fly a warp bubble into a star.
So what's the future for this field? What are you guys going to do next?
These kind of all scientific research projects are kind of stressful at the end. And at the end, you're always a bit fed up with it and you have to write it up and you have to get it working. And so, at the end of it, we were getting kind of arguing about what the equation of state for the matter should be and things like this. And we were really happy to get the paper out. We were like, okay, now we'd never do this again. This was, it took us actually, so I should say it took us 7 years to get this project finished, from the time that we were in Göttingen in my office to, earlier in the year when we put out the paper. So, it took us a really long time. And it was hard, all of the different aspects of it required us to really rethink how the simulations worked. But having had a little break now, I'm starting to feel again more enthusiastic about going back to it. And, we've talked about a lot of the ideas that, we could do. So looking at, what is the barrier to going to higher warp speeds? If you go to warp 1, where your speed of light, are you going to see some breakdown? Is there going to be some reason why you can't do that? Singularities, if we, not necessarily for warp drives, but actually just looking at, if you have this kind of exotic matter that we were modeling in other scenarios and you are collapsing it, can you generate, wormholes dynamically? Or, if you have wormholes, with this kind of exotic matter and you merge them, what do the gravitational wave signatures for them look like? I'm starting to feel sort of more and more enthusiastic about going back to the project now that we've had a small break from it.